Okay, today we are going to learn this, the Maclaurin Theorem. Okay, so far we have learned in lower and upper 6, we have learned so many functions. That is, we have learned algebraic function, exponential, logarithmic function, and then all these sine, cosine, tangent, secant, and cosecant. All these are under trigonometric function. So we have learned all these functions, and then actually all these functions we can expand them into a series, just like 1 plus x to the power n. We have expanded before during our first semester. We use the binomial theorem. So in binomial theorem, how do we expand it? This one we have learned it last year. And then when you want to expand it, this is x power naught, n x power 1, n minus 1, and then x 2 factorial x squared, and so on. This is binomial theorem. And then when we expand it, we have all many terms here, and then when you add up all the terms, it will form a series. What we call this a series. That means it make up of many terms with add up. Okay, and then here the expansion, this expansion is only valid when x is small. Okay, small, what is meant by small? X must be smaller than 1, greater than -1. This is lower 6, so we just a very brief go through only. And then today what we are going to learn, which is a better theorem, which is called Maclaurin Theorem, because binomial can only expand algebraic function. Other than this, all these binomial cannot do. So now we are going to learn the better one, which is called Maclaurin, which can expand all the theorem here. So how are we going to do this? Now I'm going to show you. Okay, so for Maclaurin theorem, okay, all the function here can be expanded like this. A0, which is this one, a constant, and then A1 here, if binomial is n x, okay, then A2, x2, a3, x3, and A4, x4. So for different function here, the A0, A1, A2, A3, A4 will be different. Okay, so how are we going to find A0, A1, A2, A3, A4 for all these different functions? So all those different functions, how to find all the A0, A1, A2, A3, A4? This is what we are going to do, and this is called the Maclaurin Theorem. Okay, so now I'm going to show you this. Okay, look at here. How to find A0? First of all, we just substitute. Okay, we just substitute x equal to 0. So when I substitute x equals 0, I will get f0. I get this is A0. The rest, because I substitute x0, the rest I will get 0. Am I right? The rest we get 0, so just forget about it. Therefore, I will get the first one. How to get the A0? A0 will be substitute 0 into the function. Okay, now how to find A1, A2? So what we do, we differentiate the fx. So when you differentiate, that is the first derivative. So when I differentiate A0, I will get 0. So when I differentiate this one, I will get A1. Okay, and then this is 1. Okay, then when I differentiate this one, I will get A2, and then the 2, I bring it down, I differentiate, I get 2x, and then I get A3, and then I bring the 3 down, I get 3x squared, and then I have A4, and then 4x cubed, like that, and so on. We still have many terms, but I will do until here. Okay, so again, here I just substitute x equal to 0. So when I substitute x equal to 0, I get f, the first derivative, not fx, f prime x, 0. I will get this one, 0. Okay, then I will get A1. And then again, the rest will be 0. The rest, because there is an x there, the rest will be 0. So from here, I will get how to get the A1. A1 will be the first derivative, and then I substitute 0. Okay, so look at this. How to get your A0? Here, how to get the A1. Okay. Okay, now we continue. Differentiate again. So we repeat. Okay, repeated differentiation. So we repeat again, we differentiate second derivative, f double prime. Okay, 0, forget about it. This one I will get 0, and then here I will get, okay, 0, forget about it. So I just differentiate this, I get a2, and then this one 1 I bring down is 2 times 1 x to the power of 0, is it? Which is 0. And then plus a3, I differentiate this one, 2 I bring it down will be 3 times 2x, and then plus a4, and then here also I differentiate with 4 times 3x squared, and so on. Okay, here after this I will get this. Okay, this is 1. Okay, this is 1. Okay, then here again I substitute x equal to 0, but this is 1. Okay, this is 1. Okay, when I substitute x equal to 0, I get f double prime 0 equals to, this is 2 times 1 a2. The rest, because this is x squared, I will get 0. Okay, so this one forget about it. Therefore, I can get f double prime 0 is equal to 2 factorial a2. So I will get a2, how to find a2 will be f double prime 0 over 2 factorial. 2 times 1, we call it 2 factorial. Okay, now we have already got our a0, a1 until a2. So now I continue to differentiate. Now I have f triple prime x, I differentiate again. Okay, this one is constant, no x, 0. Okay, when I differentiate this, I will get a3, and then this one I differentiate, I get 3 times 2. When I differentiate the x, I will get 1. Okay, and then the a4, I will get, differentiate again, I get 4 times 3 here, small times 3, I differentiate the 2x, I get 2x1. Okay, and then so on. Okay, here again I repeat, I substitute x equal to 0. I have f triple prime x. I will get, this is a3 factorial. This is 3 times 2 times 1 is 3 factorial, a3. Okay, and then plus a4, and then this is 4 times 3 times 2, and then x. Okay, here again I substitute x equal to 0. I substitute x equal to 0. I will get f triple prime 0 equals to 3 factorial a3, and then this one will be 0 because of the x here. Okay, therefore I get my a3 is equals to f triple prime 0 over 3 factorial. So this is what I get. Okay, so this is the a3. So if we look at this, of course, then if you continue again to differentiate one more time, you will get the a4 will be equal to f, this is power 0 over 4 factorial, and so on. So if you want to get the a5, of course we don't try so far. Okay, this one, that means we differentiate 5 times 0 then over 5 factorial. Okay, so this is what we will get. Therefore, according to Maclaurin theorem, it says that all the function, all those functions, as I said earlier, can be expand like this. Is a0. What is a0? Okay, look back. What is your a0? Okay, this is a0 plus a1x plus a2x squared plus a3x 3 plus a4x4 and so on. Okay, so what is your a0? A0, number 1 is f0. You see, this is f0. Okay, what is your a1? Okay, look at what is our a1 just now. This is our a1. So the a1 will be f prime 0 over 1 factorial x. That means a1 first derivative. Okay, first derivative 0 over 1 factorial. Okay, then what is your a2? A2 will be second derivative 0 over 2 factorial x squared. This is our x2. Okay, then what is our a3? a3 will be third derivative. a3 will be third derivative, substitute 0 over 3 factorial x3. Okay, then what is your x4? a4, sorry. a4 will be the fourth derivative. f fourth derivative, substitute 0 over 4 factorial x4. Okay, and of course, what is your x5? The fifth derivative over 5 factorial x5 and so on. So what we get here, this is a series, and this series can be used to expand all those functions that I have mentioned just now. All these functions can be used. So this is called a Maclaurin. This is called a Maclaurin theorem. And what we have got this series, we call it a Maclaurin series. Okay, so now after that, of course, the next video I'm going to show you how to use this, how to differentiate, how to use the repeated differentiation to get this series for different functions. So we are going to do the next video.